And Emily, you can go first if you'd like.
Okay, I'll go first.
Okay, so go ahead and share your screen. If you want Ryan to go first, also it's up to both of you.
I'll go first.
That's okay. She can go first.
Just
I give you the privilege to share your screen. You should be able to share.
yeah. Let me know if it's up.
Here we go. Yeah.
You can see it?
Yes, we can.
Okay, hi. So my name is Emily, and I am going to be presenting on a paper that I was a part of called Do Experienced Programmers Put Too Much Confidence in Comments? Before I start, I want to mention that this study was a part of MLAT, which is the Machine Learning and Affiliated Technologies Lab here at Chapman. It was advised by Dr. Eric Lindstedt, and other collaborators were Elia, Abby, Lily, Raha, and Katie. We worked on this in December of 2019 and January 2020, right before the world turned upside down. And it was actually published in a part of the conference SEEK 2021, which is the International Conference of Software Engineering and Knowledge Engineering. We had just gotten new eye tracking equipment, which I will go further in depth on in a bit. But this project was meant to be sort of like an initial exploration of what we're capable of doing with the eye tracker, and hopefully we would be able to expand on that later. We didn't really get to do much expanding on that this year because we needed people to come in for the eye tracking data gathering. And with COVID, that wasn't really possible, but hopefully in the future, that will be a possibility. So here. So source code and eye tracking. Using eye tracking to understand how programmers read code is not really a new concept. In fact, eye tracking has been extensively used in modeling how programmers visually process source code as part of software development activities. Some of the findings from past research show that programmers reviewing code skim the file until a snippet of code prompted them to slow down and review a section more thoroughly. Some of these code snippets that like trigger a programmer include things such as identifiers, inconsistent code changes, and other just confusing or incorrect code. They also found that there was a correlation between the time of the initial scan of a program and the ability to identify errors in code. It was seen that programmers are often not thorough when reviewing code. The eyes tend to follow source code from left to right, scan for methods, and then jump around to find different keywords. I know I, for one, probably I don't really know for sure, but I know that I do kind of jump around, look for keywords. I don't necessarily like follow one particular like formulaic structure. Also, difference in experience level has been looked at before in different research. Novices often would approach code as like more natural text. First, like utilizing patterns just from left to right, natural text patterns, the way you would read like a book. And then as they became more familiar with a particular programming language, such as like Java or Python, more sophisticated patterns were starting to be used. Expert coders tended to often use more broader blocks of code to understand the scope of the code, while novices, like I said, read more like line by line. More comfortable programmers will often even read from bottom. So what the program is meant to return first, so looking at the return statement or any print statements and kind of working up from there. So kind of our motivation here was researchers have found that the majority of eye tracking studies could be categorized into 5 general topics. So code and program comprehension, debugging, non-code comprehension, collaboration, and traceability. Additionally, there are surveys that have covered like over 60 different eye tracking source code studies. And they show that most eye tracking studies are based on like the same concepts being retested just time and time again with new data. So taking all of this into account, what I was talking about before about the different coding patterns that people, like the way that people read code, the patterns that they do, the maybe some of the inability to read, to see errors in code because of the way that they do it, or the non-thoroughness that they're actually covering of the code. So our research kind of incorporates that. It incorporates these 5 themes that I talked about: code, program comprehension, debugging, non-code comprehension, collaboration, and traceability. And we incorporate a new topic of inline comments. So as I mentioned a minute ago, programmers are often not thorough in reviewing code. A ton of time and practice will be reviewing code though. So it is important to be thorough. So what do we kind of do to streamline this process? We use comments. So a big motivation focusing on comments in code. And so as I'm sure you know, as I'm sure you're aware, programmers, software engineers, data scientists, we're all trained to provide meaningful comments in our code so that it can be used by ourselves later to reference the code, or by others who have never even seen the code before. So well commented, accurate, easily understandable, comprehensible code is oftentimes just as important as code that runs efficiently and correctly. Maybe not just as important, because we obviously want our code to be running correctly and no bugs or crashes to be happening, but in the long run, it is very important to have really good code quality and commenting style. So obviously, because if there's a large bug in a program or a project and you go back and you try to fix it, good luck if you haven't referred to that code in a while, or if you never have because you didn't even write the code, trying to diagnose the problem if it wasn't well documented. In professional practice, software deliverables are often accompanied by substantial amounts of documentation. This is both by comments in source code and in technical documents, APIs, and more. Again, comments are used by both the programmer who wrote the code, who may need to use them going back to refer to specific section of codes, or other programmers who need to reference, edit, refactor, or use the code. All of this being said, it's obviously that comments need to stay up to date and accurate, or else things can get confusing. And all of this leads to kind of our main questions that we were trying to answer, which are: how much attention do programmers pay to source code comments when tasked with comprehending a piece of code that they did not write? Also, our second question kind of ties in with the first one: does experience level impact the level of reliance on confidence a programmer has in comments when faced with a program comprehension task? So in order to answer these questions, we recruited a small sample of 14 participants. The only requirement that we had with these participants was that they were experienced in coding and were comfortable to at least some degree with Python and Java. So because one of our aims was to find whether experience level played a role in trusting comments, we recruited an even split of participants in our study. So we recruited ultimately 7 experienced coders and 7 novice coders. And so here you can see a breakdown of what kind of categorized an individual as either experienced or novice, and then a breakdown of the participants that we actually got. So novice coders were someone who had less than 4 years of coding experience and no industry. The median of the novice coders that we had 1 year of experience, and on average, they had 1.9 years of experience. And then just another side fact about them, they averaged about 2 hours of free coding time per week. And then so for our experts, these were coders who had 4 or more years of coder experience and have had industry experience as a software engineer. there was a big difference in the median and means of novice and experienced coders. The mean coding experience for an experienced coder was 12.3 years and the median was 7 years. And I also want to mention that throughout this presentation, experienced and expert will be terms that are used interchangeably. So whenever I say experienced coders, I mean the same thing as when I say expert coders. So in terms of participants, I think it's important to note that all of these were recruited from Chapman University. So either students or professors, they were all at Chapman. So this could definitely cause some bias in terms of how the participants choose to read a program and the emphasis that they put on code. So perhaps all students are taught to put a certain amount of focus on code because they all had the same first computer science class or with the same professor. So maybe this professor taught to do a specific coding style and to focus on them to a certain degree. So thus, this means that any results obtained from the study are preliminary because they may not be, the results that we obtained may not be universal across people who came from different universities, different workplaces, or just different coding experiences. So addition to this sort of shortcoming, clearly a sample size of 14 is not substantial by any means and may definitely further the bias. So, because the reality is that a small sample size is a restriction on the certainty that we can place on any of our results. So in the future, expanding on this study with a much larger pool of participants and with a larger array of backgrounds would definitely be important and something that we'd want to do. So as I mentioned before, this experiment was using an eye tracker. And the eye tracker that we used was the iLink 1000 Plus. As I've mentioned, the primary way that we studied how a programmer reads was through the eye tracking device. To use the eye tracker, there's several steps that you take. The first thing that you do is you have to calibrate it to the person's eye that you'll be tracking. You can see, well, this is done by putting a sticker kind of in between their brow bone and setting up a participant in front of a camera and in front of a computer screen. The computer screen we would ultimately use to show the code to the participants so that they can read. But first, like I said, we had to calibrate it. So we can see here on this slide, as modeled by our lovely classmate and my collaborator on this project, Lily, that the camera focuses on the participant's pupil. You can kind of see in that picture that a blue highlight is around her pupil. And that shows that it is correctly kind of zoned in on her pupil and it's going to be able to track it. Then the next step is to calibrate it, which you can see on the bottom screen. You can see that there are several dots on the screen. And what happens is it starts off with a blank screen and one by one a dot appears and then we instruct the participant to kind of fix their gaze onto the dot as soon as they can and as accurately as they can. And different ones will appear. And once it's done, this screen that you see right here with all of the dots appears. And you can see there that there's a main dot and then another dot. And that shows how far away or how accurate the gaze is to the actual dot. And you can see that there's a very small margin, which is a good thing. It means that it's calibrated successfully. If there was a large margin between the actual gaze of the participant and the dot, then we might see some problems there and we'd have to recalibrate it. So that's in general how the eye tracker, the iLink 1000 Plus works. And then the iLink Data Viewer is another software that's included with the eye tracker. And this just generates video, statistical analysis, and visualizations such as heat maps to further analyze our results. Okay, so now we'll go into the experiment that we did. So each participant, when they arrived, filled out a brief survey relating to their demographics, their experience coding, and then they were calibrated on the eye tracker as I just showed how that was done. And then they were ready for the actual experiment. The experiment consisted of the participant viewing a series of images that contained source code. And the source code was a simple, straightforward program. We didn't want any like trick questions or confusing code. The participant was then asked to verbally state what the program did. And in order to not kind of mess up their flow of what they were doing or to take their eyes off of the screen, because that was one part of the eye tracker, you can't like move around too much, you can't look around, or else you'd have to recalibrate the whole thing. So in order to eliminate that issue, we just recorded their verbal responses, and then we would later use those in tangent with any eye tracking data that we got. And they were given as much time as they needed to review the code to kind of hopefully give them the most natural environment possible. So in this series of code samples, there were 4 that we cared about that we showed them. And each of these 4 contained single inline comments. And the catch was that 3 of the 4 source code samples that we showed them contained misleading comments, where if you trusted the comments, you would answer incorrectly about what the program outputs or what the purpose of the program was. So both of these images here are images that were source code that we actually used in our experiment. Both of these contain misleading comments. The first image that you see on the left shows comments that actually show the opposite of what the program is doing. So it says that it is given even numbers when actually it's odd numbers, which should not be too difficult to understand because it's I mod 2 doesn't equal 0, which is not what the comment is saying. And then the second image on the right is actually just showing something that does completely something unrelated to what the comment is stating. So if you were to focus on the comments, you would definitely get the purpose or the intent of the program wrong. If you were focusing more on the actual source code itself, you should be able to, with not too much difficulty, be able to understand what the program is doing and answer it correctly. So well, let's look at some of the results of our experiment. So the results of the experiment came from a combination, like I said, of the data retrieved from the iLink data viewer, such as statistical results and heat maps, and the verbal answers given by our participants. So these 2 tables display some of the results that we saw. The first table that we see on the left is relative time spent focusing their gaze on the comments. In all cases, the percent of time on the comments versus the rest of the source code was higher for experts than novices. So on average, experts spent about 34% of their times on comments, and novices spent about 26% of their time. And the difference there on average was experts spent around 7% more time than novices did. And this is interesting because I'm not sure, we'll talk about it a little more later on, but it's interesting to see that experts actually focus more on comments when they would probably be more likely to easily understand source code quicker than novices would be able to. And the way that we indicated these times was we selected a range on that image. Like for instance, if I go back a slide, on this image here with the source code, we would basically select, so pretty much similar to what we had with this red outline here, you'd select the comments that you'd want to see, and then the iLink data viewer calculates the time that the gaze was fixated on that region that you selected. And so that's where we got the average of 33% or 34% looking inside that region that we selected versus the outside region. So this table was obviously created using that iLink data viewer. And then the next table is our portion of coders that, I don't know why it's blocked here. Anyways, this is the portion of coders that were misled by the comments. And so this was more so by the recordings that it's when I talked about our verbal responses. We use different kind of keywords and triggers to understand whether or not they were misled or not. And in many cases, actually in every single case, on average, the experts were more misled than the novices, which is very interesting to me. Like for instance, question 1, 100% of the experts were misled, while only 57% of the novices were misled. Question 2, 71% versus 28%. Question 3, there was no misleading comment, so it was not applicable in this situation. But then again, question 4, it was 85 versus 28, which is a pretty significant difference in my opinion. Okay, so visualizing the results a little more in detail and with our heat maps. So in this slide, we see there's aggregate heat maps for question 2 for both experts and novices. And to get a better idea of what we're looking at, I'll talk a bit about how these heat maps were constructed. So using the iLink data viewer, we produced heat maps for these images inspected by each of the subjects. So we generated heat maps for each of the source codes that the subjects viewed. To create these heat maps, we applied 2-dimensional Gaussian distributions to each of the fixations. The center is the location of the fixation. The width it was regulated by a sigma value of degrees of visual angle, making it so that the area affected by the fixation increases as the value increases. The duration of the fixation then weighs on the height of the Gaussian. The 2D Gaussian it was then added to an internal map by adding weight to the areas of the map. And then this process was then applied to all the fixation points and was normalized. I don't have exact formulas or calculations at this point of what we did, but this was the general idea of how we generated these heat maps. Okay, so back to these results. So we can see that the expert coders appeared to read the first few lines of code and then sort of stop at the comment line without looking much beyond that. We can see that the novice coders, on the other hand, tend to look at the whole breadth of the source code. So you can look at the red area. For the novices, they spent a lot of their time on the if statement, where the expert coders did not. So you can see here that for the novice coders, the red, the kind of central fixation point, is definitely shifted down more. And they're looking more down in this area where the if region and then what the A1 equals I actually does. Here, their gaze is definitely lifted higher up, and they kind of are more focused here, stopping where the comments are. They hardly even enter this region of what the if statement actually does. And again, to reiterate, as I stated earlier, to confirm what is viewable on these heat maps, we listen for key information when the participants are given their answers orally. So buzzwords when describing the program, such as prime versus not prime, indicate to us whether or not they're trusting the comments. And of course, answering incorrectly or correctly, if they give numerical answers, immediately tells us that they trust the comments or not. And then, so we're gonna go back to question 1, which shows something very similar. So for question 1, experts again focus on the upper parts of the source code, stopping where the comments stop. And we can see that their eyes view the comments also by the width, unlike the novices. So the experts here, you can see that the comments in this case expand further out. And you can see that their gaze, they fixate a little more further out this way. Here, for the novice heat map, they don't really even extend far out here. They don't look much at the comments at all. They're definitely, again, more focused on what's inside of the actual purpose of the code, the if statement. So we thought that experts would be less likely to be misled by the comments because they're more comfortable reading the code, but this was not the case. So our discussion on this, obviously this is not what we hypothesized. The novice coders seem to trust the comments much less than the expert coders do. So why could this be? Well, one reason may be the testing environment. a student may feel more pressure to answer correctly simply because they feel like they are being tested. And that is just a stressful situation in many cases, especially for students. Um, we did make sure to instruct them to not worry about getting the answers correct, um, as much as they, and just to try your best to view the code as normally as you would, as if you were just sitting in your house reading code. But obviously that's much easier said than done. Um, and that ultimately is definitely another kind of, I don't want to say shortcoming, but it's definitely a factor that could inhibit the accuracy of our study. Um, Next, another reason, experienced coders just have more industry experience. And the fact of the matter is industry experience is when you actually get used to really relying on comments. As a student, it's less likely that you'll actually have to have a reason to ever go back and read comments that you wrote, because it's much shorter programs and you don't really go, we usually just focus on single assignments at a time, and we don't need to remember something that we did from a year ago or some super large programs. So we might not just be used to reading code and or reading comments as much. We're just more comfortable reading the code itself. Experts, on the other hand, are much more likely to have to rely on comments more often, so their trust in them are probably higher. And finally, experienced coders are probably just more confident in general, confident with their coding, confident with their reading code and comments. So they're not less stressed about getting the answer right or wrong. They're just reading the code and stating it like they feel like it is without the stress of like that testing pressure. They're just already confident in where they're at. So while none of these hypotheses of why this could be were actually tested, I think they would definitely be a topic that's worth exploring in the future, for future studies. And definitely, yeah, just more interesting information on this topic. And this leads us to more future works. So I think it could be definitely interesting to investigate this further. Specifically, if the programmers utilize the comments in the same way, would they utilize them the same way if the scope of the program changed? So if we use very short functions in this experiment, would that change with more long or more complex programs? You know, the longer that it becomes, the less likely that you're going to want to actually go through the entire program and try to comprehend every line of code. It's just not feasible. So obviously, I think comments would become much more important and more utilized. So would we even see the same novice coders that we saw utilizing no comments here and really relying on the code itself? Would we see them shifting their focus to more comments as the code shifts from more straightforward to more increasingly complex programs? I would hypothesize that that would probably be the case, but that I think would be worth further investigation. I think it could also be worth looking into if commenting style plays a role in the programmer's place in comments. Would our experiments have produced the same results if we used like descriptive block comments at the top of each function instead of single inline comments? I know that I tend to write single inline comments, and I think that's because that's kind of what I was initially taught to do. But when I really think about it, when I'm reviewing code, I think I actually prefer to read block comments. I think they just make more sense to me. They're more organized, clean, and descriptive, and they definitely are just more helpful to me in understanding code in general. So I think I would be more likely to trust those, but I'm curious to know if this actually changes the way that others trust comments as well. Lastly, I think it would also be interesting if coders are even aware of how they utilize these comments. Maybe expert coders are so used to reading comments in code that they're not even realizing that they're doing it. It's sort of second nature, and they aren't aware if they are or aren't using the comments. We could answer this question simply by conducting a similar experiment and asking the participants at the end of the study how they utilize comments, or did they read the comments? Did they not? Maybe they'll think that they didn't really use the comments, but they actually did and were misled by the program. Yeah, and so beyond that, obviously, I think we would definitely like to look at other things beside comments as well. Like I said, there have been extensive studies on eye tracking and people's gaze while reading comments, the patterns that they use, reading code and the patterns that they use. But I think that there's definitely more that could be done there. And why? Well, there are applications that we could use. Yeah, we could do some sort of customized IDE that is customized to how a coder views code. So maybe popping out certain parts of code that are important and that a coder tends to skip over could be helpful to kind of draw their eye on the focal points of the code and kind of streamline the process of understanding code, where bugs could be a factor that maybe they aren't catching. Also, maybe it could warn a user to change a comment if like a block of code has changed too much, because this is definitely one of the reasons why a comment could be wrong. Perhaps a coder was making changes to a program, they're on a roll, they don't want to stop and change the comments after they change the code, and they'll think, oh, I'll come back to that and do that later, and then they just never do. So obviously this can make a comment wrong at that point. It can make it completely irrelevant. And in the future, when you or somebody else is trying to go back to the code, it could cause a lot of confusion, especially if it's a large program. And like we've seen here, people tend to, expert coders especially, tend to trust comments oftentimes over the content of the code itself. And then of course, another quick way that you could apply this would be to apply it to your own coding and commenting practice. Make sure that your code is straightforward enough to where you can understand it without, or with just minimal comments to avoid confusion later on. But of course, even if you can understand it, it's always good to have comments for the future and for others. So keep those comments clean, clear, concise, and keep them up to date as you change your code. And that's pretty much all I have here. Here's just some of related papers and papers that we used in our paper. And yeah, that's
Great.
it. Thank you.
That's amazing, Emily. Thank you so much for this very rich presentation. Like that was great. Like, I didn't want to stop you. We have time maybe for a question or two very fast, so that we give enough time for Ryan to do his presentation as well.
Okay, thank you.
Do we have any questions for Emily? There's something in
There's one in the chat.
Yeah, I was reading it right now. Did you see that, Emily, in the chat from Riley?
No, I'm trying to get to it. Hang on.
You may have mentioned this area, but were the experts and novices given the same amount of time to analyze the codes, or was there not a time limit?
Oh yeah, there was no time limit. We wanted to make it as like natural as possible. We also emphasized that you didn't have to get it correctly. We just really wanted more so to understand their process. So a lot of times they even kind of explained, we didn't tell them they had to do this, but they could even like explain as they were going what they were seeing and like what they thought the program was doing, and changed it over time as they were reading it. But there was no time limit.
Okay. Riley is sending you a follow-up. I wonder if the experts viewed both the comments and the code more than novice, and were just more confused.
That's a good question. No, actually, I didn't include this in the presentation, but overall, the amount of time that someone spent on looking at each of the source code blocks, experts as a whole spent more time on each slide than the novices did. So yeah, I think they just definitely kind of read through it once they saw the comment, kind of just like fixated on that, trusted it, and moved on. While coders, while novices kind of went over it and over it and over it again until they felt most comfortable answering the questions.
Great. That was really great, Emily. Thank you so much. Let's move on for Ryan's
Yeah,
presentation. You can stop sharing right now, and Ryan, the floor is yours.
I'm not a stop shit.
Can you guys hear me okay?
Yes, yes, we
Okay.
can.
Hello, my name is Ryan Richardson, and this is a project that I worked on for 520. I affectionately call it non-destructively describing discrete density domains in workable wooden wadges, alternatively making meaningful metrics without compromising cold cops' corpses, which basically means how do we measure the density of a wooden object or a tree without killing it. So some background of how this even began as a project. I was bored over summer, was thinking about how to make a fair six-sided dice, and I was thinking of making it out of wood, just because wood is pretty cheap and easy to get. And when you look into the manufacturing of a fair dice, you find that the shape and the materials used are pretty much the most important things. For shape, we know that there are kind of 5 perfectly symmetrical three-dimensional objects that are kind of guaranteed to create a fair dice when it's rolled. But that's assuming that the material it's made out of is neat or consistent. This is really in regards to the material's specific gravity, which is kind of an antiquated or an older way of just describing the density of the object. Specific gravity is just density compared to a volume of water, and density is the volume of an object compared to its mass. So when we're working with wood, again, it's cheap, it's easy to work with, and there's really low cost of failure. If you mess up, you can easily restart, and you're not spending a couple $100 on metal or something like that. But there are concerns about the consistency in wood, especially if you're comparing across species. And there's even issues within the same species of wood. If you've got a white oak tree grown in Texas or wherever, that's going to be very different from a white oak tree in Maine. And that's because as the tree grows, the distance between its growth rings are going to be dependent on how many nutrients were available to the wood. So it's going to be either less dense or more dense, kind of depending on the quality of the environment it grew up in. And these things are really so distinct that, you know, we can study climate change and other things like drought or toxic soil conditions just by looking at fossilized remains of trees, because they give us a very accurate kind of representation of the landscape that that tree grew up in. So when we are talking about creating dice out of wood, you know, we need to ensure that the material we're using is kind of like consistent throughout the entire piece. And again, we do that by looking at the object's density. And when we're talking about kind of measuring density, initially this was really pretty basic. We started measuring density by looking at the volume of an object compared to the mass of an object, and that was it. And that's really great and that's awesome, but that really is kind of limited to what we like to call neat objects, things that are easy to measure the volume of, things that are easy to measure the mass of. And we don't always have a way of comparing the density of objects to each other. And I think one of kind of the famous anecdotes about this is Archimedes taking the crown of a king to see if it was made out of gold or if it wasn't made out of gold. And what he did, he placed, you know, something of the same weight, a lump of gold of the same weight as the crown, in water, and used that to kind of get a gauge of comparing the density of the objects of the crown. So we can measure density like that. We can measure density by taking an object and looking at its displacement in water, or we can just weigh it and get the volume of it. Obviously, if it's a cube, like a six-sided dice, that's easy to get the volume of, it's easy to get the weight of. But the issue here is that that's really only giving us a value for the average density of the object. That doesn't tell us anything about its internal structure, and that might not be good enough. And to kind of demonstrate that, I have this wonderful diagram here. And if we're looking, imagine that this is the top of a cube, right? And it's a cube of wood. And this teal area is an area of consistent density. But this red area is an area that is not consistent density. Maybe it's a knot in the wood, or it's some other defect. And we might not be able to see this, when we're actually looking at the dice on the side. But if we were to roll this dice over and over again, this face that is more dense is going to land on, it's going to bias the dice. It's going to land on that side more often than not, right? So we can't just look and assume that an average density value is going to be good enough. So what do we actually do to get a good density reading throughout the entire object? And that leads us to kind of we have a couple options that we can explore. We do core drilling into the wood, and we can pull out the core and we can see, okay, is it consistent all the way through? Are there any defects? We can use electricity and measure electrical resistance, and that gives us an idea of density. We can do X-rays and radiography, which gives us, again, internal structure, and we know that we can kind of use that to look at, again, any defects or voids or things like that that might be impacting density. We can use ultrasound, which is similar to using light. It's just using sound. So we're using a physical force instead of an electromagnetical force. Or we can have some fun and we can just hit it with a hammer and we can see what happens. But what out of all of these is actually suitable? Core drilling is okay, but it's destructive. If we're core drilling a tree, that can kill the tree or at least severely harm the tree. If we're trying to make dice, core drilling might work, but only if the dice we're making is smaller than the core that we drill. And again, there could still be imperfections in that tiny area that we cut out. We can use electrical resistance and use electricity to measure density, but this leads to surface decay. This is heavily impacted by particulates that might be in the wood and humidity. And if you do this over and over again, this starts to be destructive. And if you start burning away at the surface and damaging the surface, you're basically losing some of the carbon in the wood, and you are biasing your dice where you take your measurements. So that's not really an option. X-ray is probably one of the more accurate, but it's very expensive. It usually takes large equipment, and it's not very portable. So again, if you're doing this on like a tree or a large block of wood, you can't really do this X-ray, this radiography in your garage. You need to take it somewhere, which isn't always feasible. Then there's other forms of radiography, which are really good for like surface mapping and kind of getting really fine details in the surface of an object, but it doesn't penetrate deep enough to tell us about the internal structure. Again, hammers are fun, but they're only so accurate, and obviously we can still damage the piece that we're working on, so we're not going to go with that. And that really only leaves ultrasound. Ultrasound is kind of a well-established thing. It's relatively cheap, and it doesn't take a lot of equipment. You can get pretty much everything you need for under $100. So it seems like that's probably the way to go. Now, ultrasound isn't any different than normal sound. It's just sound at a frequency above what humans can hear. Comparatively, the opposite of that would be infrasound, which is things too low frequency that we can't hear. Ultrasound isn't necessarily safe on its own, but you don't get into destructive ultrasound until you're talking about hundreds of megahertz, and that's when it starts to get destructive, and you don't really want to do that. But we know we know where those limits are. They're pretty well defined. So we don't, as long as we're staying within our limits, we're pretty good. Typical ultrasound devices start at about 20 kilohertz. And again, they can exceed, hundreds of megahertz. And what we're looking for in this case is we're looking for a frequency that is high enough to penetrate through our estimated densest part of the wooden object, but not so high that it totally goes straight through the object and is just unaffected by the density of it. Because if you use a really high frequency ultrasound, you'll just kind of blow past and it'll be very hard to take any accurate measurements of. And if you use too low of a frequency, you'll start getting kind of rebounding inside the object that's going to mess with your measurements. So we need to be careful about the frequencies that we actually use. So a big part of this, obviously, once I settled with using ultrasound, was how do we actually create an ultrasonic pulse, and how do we read that, and how do we actually use this? Ultrasound is created with something called an ultrasonic transducer. What these are they're basically typically little ceramic discs that you send electricity through, and they'll start to vibrate. And that vibration imparts a physical force that we then experience as sound. And it'll vibrate more often, it'll at a higher frequency and at a little bit of a higher amplitude in some cases with the more current you pass to it. And that's good because it also means that we can kind of flip this around and we can use a transducer to receive a signal. So when if we have it in like a receive mode, when the transducer picks up that vibration, it's going to convert that into an electrical signal, into a current, and we can measure that current to kind of get a frequency reading from that receiver. So this is really great. This is something that, sounds like it'll work. Maybe we can pass in a frequency from a sender and get it to a receiver and track the time of it. So ultrasound is kind of the way. It's really kind of the way to go here. Now, there's a question sometimes about, okay, why would you use frequency of the sound over amplitude, or kind of how loud it is essentially? And the reason we use frequency is that sound generators have like what are called like near and far field effects. And the amplitude of that sound changes pretty drastically depending on where you're measuring it. And it can be really difficult to literally kind of denoise this and troubleshoot if something's going wrong, or to get like an accurate picture if you're only using the amplitude. So that's why we end up using frequency, because the frequency of the tone isn't going to drastically change. So we can use that for our reading. So how do we actually set this up to actually measure it? So what we're going to do, or what I did, was we set up 2 or more ultrasonic transducers on opposite sides of the object. And then we're going to send a pulse through a receiver, or an emitter. And we're going to track the time of flight it takes for basically the time it takes for the receiver to actually pick up that pulse. And as long as we know to an accurate degree the distance between those sensors, we'll get a time value and a distance value for that travel time. Obviously, distance and time, we can get speed from that. There was existing research for using ultrasound for looking at wooden objects, and usually the best to use for wood is somewhere between 300 kilohertz and 1.6 megahertz. So for me, I ended up using just 1 megahertz, just because those are some of the more common transducers that you can get and they seem to work pretty well. And then once before I go into that, so we can either do this with 2 transducers, one on either side, or we can kind of create a phased array of transducers with multiple receivers, and I'll kind of show that in a minute. But before we kind of do any of that, we need to talk a little bit about how we actually place these on an object, because the placement is going to greatly impact the accuracy of our readings, and it's going to define what kind of math we need to do at the end of taking all of our readings to actually get a real density value out of this. So there's kind of really 2 main considerations when we're talking about transducer placement. I'm going to go to another crudely drawn example, but essentially what happens is, if we imagine that this is our emitter, the emitter is going to send out the ultrasonic frequency in a cone, usually about 15 degrees on either side. And it's going to emit, it's going to emit a sound wave that's going to be traveling along that will eventually be able to pick up with a receiver. Now, something that we need to consider, though, is that in this case, we see that here, our tone's going to rebound off the edge of our block, and we're going to start getting interference coming this way along our measurement. So with this, it means like we need to be careful, and we need to be kind of cognizant of where we actually place these emitters and our receivers so that we're not getting this kind of interference from the boundaries of the object. Now, this, at the end of the day, this doesn't end up being a huge thing that we need to worry about. These beam profiles are pretty, and these beam characteristics are really well understood. And any transducer is going to have a data sheet that kind of tells you exactly where you'll get the most accurate readings. So we just need to follow that and kind of place it accordingly, and we won't really run into this issue. And we can kind of mitigate some of this behavior if we know kind of the time of flight it would take for this rebound to actually start interfering with our readings. But it just ends up complicating the computation at the end of the day. So it's not, if we can avoid it, we will. So a better setup is going to be something that looks a little bit like this. We'll have we set up an emitter on one end of our block, and it's going to send out, again, we have a 15 degrees on either side of center. That's going to send out a pulse. And we're going to have 3 receivers, receiver 1, 2, and 3. And we'll measure the time of flight from this first emitter to each of these points. And what we'll get at the end is we'll essentially place this on a digital representation of our block of wood. So that's what this second drawing is essentially showing. With one pulse, using one emitter and 3 receivers, we now have kind of three readings for time of flight throughout the block of wood. Now, all that we need to do now is repeat this. So now if we move this to somewhere where we're now interacting with our damaged or more dense piece, whatever you want to call it, we're going to do the same thing. We're going to emit our pulse, we're going to get it to each of our receivers, and we're going to get a time of flight. And in our digital representation, we're now going to have 3 additional readings that are going to have a different time of flight for that reading. Now, initially, we might think, okay, can we just take these readings and go straight to density? And the answer is kind of, but not fully, and we'll kind of get into that. So how do we first convert that speed of sound into a density reading? We know that the speed of sound is affected by physical processes. Again, sound is a physical force, a physical vibration that we experience as actual sound. It's not like light, which is different, electromagnetical, right? So we know it's affected by a physical process. And because of that, it kind of, it obeys some pretty nice, it obeys some pretty nice constraints for us that have been well established. We know that sound travels faster through denser objects. And we know that its speed will increase in proportion with the density of that object. And that's what's represented by these 2 equations. So the speed of sound is essentially equal to the square root of what's called the Young's modulus over density, or density is equal to our Young's modulus over the speed of sound. Now, what's Young's modulus, though? Young's modulus is essentially how a material responds to a stress or force across a given area. And it's the ratio, it's the relationship between the amount of stress applied to the amount of strain that is experienced by the object. And that's what these 3 equations are essentially representing. So to measure Young's modulus of elasticity, all that we need to do is we apply a force to an object, and we measure how much that object deforms given that force. And we'll get Young's modulus of elasticity, and we can plug that into our equation. Now, that sounds very easy, and we think that it can't be that easy, and that's because it's not. Wood is, again, not a normal or standard material, and the way it reacts to physical force is going to be dependent on the direction that that force is applied. If wood has a grain, right? And if you apply a force parallel to the grain, it's going to react differently to a force applied perpendicular to the grain. And that's, both of those are going to change if it's applied along the end grain or perpendicular to it. And this kind of behavior where a material reacts to stress differently depending on the direction of the stress applied is called anisotropy. So this wood is what's called an anisotropic material. Thankfully, wood is a nice subset of this called an orthotropic material. And what orthotropic materials are is essentially, it means that if I apply a force on the left side of this object, and then I come and I take a reading here, and then but if I apply another force in the exact opposite direction, the wood's going to behave the same, which is really good for us because it means that we don't need to worry about taking readings in both directions. And it simplifies some of our future calculations by allowing us to kind of it essentially just reduces the amount of readings and the amount of stress values that we need to test. So how do we actually kind of distill this difference into something that we can then plug into our previous equations? So some very smart people that studied tensors and differential geometry and material science discovered something called Hooke's law. And what Hooke's law does is it extends our initial equation of the Young's modulus into a ratio between, or a relationship between Young's modulus, something called the Poisson ratio, and a shear modulus. And all that these are really doing is it's just saying that, again, if I have a 3D object, when I apply a force in this direction, I'm going to get a stress outward in the two orthogonal directions, and I'm going to get a transverse force on the object. And that's what the additional, that's what the Poisson ratio and the shear modulus are essentially controlling for. So we can take these measurements, but the nice thing about wood being an orthotropic material is that if we control our sensor placement, and if we control our sensor placement to ensure that the path of sound is basically going across a plane or a slice of our wooden object and is not crossing the grain in either direction when we take the reading, we can basically distill all of these down to a single value, a single elasticity value in the direction of the force applied. And I'll kind of show you what that looks like once it's all kind of put together. But this simplifies the math that we need to do quite a bit. Now we can extend our sensor placement a little bit, and we can kind of do this whole 3D reading, but it's not a necessity. So now that we kind of understand what we need to do, how do we actually put this all together? So the first thing that we're going to do, we're going to take an accurate surface measurement of the object, and we're going to identify where we want to take our density readings. We're going to place transducers on the object. We're going to super glue them to it because super glue is really easy to remove, like actually. And then we are going to mark the direction of force. We're going to utilize Hooke's law. We're going to take our ultrasonic readings, get our time of flight, and we're going to convert that to density. And then we're going to move our transducers, and we're going to do that over and over and over again. And what we're going to get is a slice that looks a little bit like this. And I know I've kind of primed you to look at it, but what you kind of see is that these areas here are a little bit darker. The readings that we took in this area are a little bit more pink and purple than they are blue, right? So with this, we can do some pretty clever, we can do some interpolation based on the polygons created by our measurements. And we can also do some other controls where we essentially look at the ratio of higher density measurements to which would be this area compared to our low density measurements, which would be this line against all of these other teal cross sections. And we can kind of modify our readings and control for that a little bit to get to create like a map of density of the object. Now I don't have a drawing that actually shows what that would look like when it's actually interpolated out, but I do have some actual readings of when I actually did this on a block of wood, and it just kind of, I know we're kind of running out of time, but it just shows how it kind of puts everything together. So here we had a 30 centimeter by 30 centimeter square, and we took 3 readings, 1, 2, 3, in these 2 directions. And we only looked at at one slice. And what we got is for the readings that were taken in the X direction, we got these 3 times the flight, and it was 10 centimeters. So that is converted to this speed meters per second. We took an elasticity measurement, which was taken by applying a hydraulic press to the wooden object and applying about, I think it was 5 tons of force, and looking how much it deformed. And then we can take that, plug it into all of our equations, and get an average density measurement here. And then we do the same thing in the Y direction. But you'll notice that in the Y direction, our time of flights here are significantly different. You know, we are 10,000 nanoseconds or more faster in the Y direction than we are in the X direction. And we are about 700 meters per second faster in that direction than we are in the other direction that we measured. But the elasticity measurement, I believe this was going perpendicularly to the grain, is higher as well. And because it's higher, when we actually get a density value, we end up getting, you know, something that's along the lines of our previous density values. This was done on a piece of white ash, and the true density values for white ash at 12% humidity are between 40 and 53 pounds per foot cubed. And that's essentially what we found, or what I found when I did this. And then we can extend this, and we can do some interpolation on it to kind of convert, again, the polygons that we saw into a 3D objects if we do multiple of these slices. So future improvements, something that we can do. Obviously, the more measurements you take, the better it's going to be. If we actually do multiple slices, we can start doing 3D interpolation, something like trilinear or tricubic interpolation, to get a much better kind of idea of the internal surface of the object. I initially just did nearest neighbor because it was easy, but it loses a lot of nuance when we do that. And then we can also kind of make a more robust penalization or reward system, again, for the cases that, again, like I said here, where we look at the number of times this measurement here crosses a higher and lower density field, essentially. So that's ways to improve it. And something else that we could do if we really wanted to is, instead of just looking at a single slice with each of these readings, we could look at so if this is an emitter, the emitter does a 3D cone, right? So what we could do is we could also have receivers that are stacked on top of each other and get readings kind of up and down the block of wood. The issue with that is, if we do this, we can't control away for all the other elasticity values. If we did this kind of 3D measurement, we would have to take into consideration the shear modulus and Poisson's ratio and everything else, because the way the force is traveling is going across different types of grain and in different orientations. So, I mean, that makes things more complicated. It might make it more accurate. But, you know, at the end of the day, doing the slicing ends up working pretty well. So that's it. That's the end of my presentation.
Amazing, Ryan. Really, really great work. Is this part of an ongoing project where you are going to be like building the model itself and like, you know, creating this three-dimensional model that you mentioned or not?
No, this was something I really just did in my spare time. And then we had to do the mathematical modeling project. And then I just
Cool.
decided to
So
convert
this
this
is
into.
how you spend your spare time. Yeah, I like that. But is this like, you know, can be part of a bigger project where you can like investigate, because it seems very interesting.
I would like to. Part of the, so I like when I did this, I created like a small, I used like an evaluation module from Texas Instruments that it would allow me to take some of these readings. I would like to have gotten something that was a little bit more accurate built. The issue is that once you start getting into some of the more accurate time of flight readings with the emitters and stuff, you're looking at, you know, tens of thousands of dollars to have someone build that for you. So from my perspective, you know, I was able to do something that was like a hobbyist for pretty cheap, but if I wanted to make this into something more robust, I would need to start, you know, putting more funds into it.
Yeah, let's look into that. We have a couple of minutes left. Do we have any questions from the audience? Both presentations today were really rich and really great. So I really appreciate Ryan and Emily's talks today. Any questions? Okay, for me, that was great, Ryan. Thank you so much for your presentation. Thanks for everybody for being here today. And feel free to reach out to me if you have any questions or any issues. And I will see you next week.
Thank you.
Bye, guys.
Thank you. Good, Professor.